Okay, so let me just remind you about the Pathways Tutor Center. This is going to be your best source for help in the course. It's not perfect, but it's going to be the best thing you can find. Okay, so the people there, we're doing our best to train them. Okay, again, it's not perfect, but other math tutors may not be familiar with this curriculum, and they won't be able to help you as much as the people here will. Okay, so it's open. So these are our office, our hours there, but it's open like 9 to 6 Monday through Thursday and 9 to 1 on Friday. Okay, so you can go anytime. All right, take advantage of that. That's a really good resource. Our exam number 1 is a week from today in recitation or the following Monday, depending on when you have recitation. You're going to go 15 minutes early to have plenty of time for the exam. So go 15 minutes early, so you go at, 10:15 instead of 10:30. And then hour and a half should be plenty of time to complete the exam. Okay, any questions? Any other announcements that I should make? You think of anything? Okay. So PSA 21, that's in the basement. If you've had a math class before and you've gone there to take tests, that used to be the testing center. It's the same room. Okay, same room. They have tables up in front now for tutoring. Okay, so let's open up your book to page. We'll start with 88. As you do that, what is a quantity? What is a quantity? Everyone think to themselves. You should know this. You should know what a quantity is. We said in the first day, we said this class is all about quantities from start to finish. So we should know precisely what a quantity. Quantity, 8.6. Is that a quantity? All right, what is a quantity? Measurable attribute of something, right? Like something, so if you have an object, it's something pertaining to that object you can measure, okay? Like, if I'm the object, we can measure my distance from the wall, okay? We can measure my weight, okay? This class could be the object, and what are some quantities that we could talk about for our class? Volume, what do you mean? Volume of the room. Yeah, so I meant that's the students, okay? So if we talk about this room, we could say the volume or capacity of this room. But if the group of you as a group of students was the object, then what could a quantity be? Average height, volume of the students. Number of students, okay? So these are all measurable things about our class. So what do quantities have to do with functions? So now we're starting to talk about functions. What's the tie-in from these measurable attributes to functions? Not quite. Right, so functions are about what? Two things. Input and output. The input is what kind of thing? A quantity, right? The input is some quantity, like time elapsed, distance, volume. And the output is some other quantity. Okay, so like we started with the open top box. The input was side length of a square cutout. That's a quantity, and that's the input into the function. And then we looked at different possible outputs or we could create functions based on that input with different output quantities. What were some output quantities we could look at if our input was the side length of the square cutout? What were some? Volume of the resulting box. What else? The length of the resulting box. The surface area of the box, right? So there's all these different functions we could create with that particular input based on choosing some output quantity, okay? So that's how this works. So you're looking at number 4 on page 88. I want you to do A through E, okay? A through E. Whenever it says, find the value and then interpret, I want you to do the other way. Always interpret the expression first. Say, what does this expression represent? And then once you have that down, then get a number. Okay, so if I ever ask 2 questions like that, interpret first, and then find the value. Okay, go. You can work together. Okay, let's see. Is it Jessica? Jessica, is that you? Did you identify the input and output of this function?
Yeah, I said the input is time.
Input was time since January 1, and output John's weight. Okay, so if I'm just identifying quantities, remember it's okay with quantities to not have the units because a quantity is just that physical characteristic. We're not putting a number on it yet. So if I just put time since January 1st and John's weight, that's okay. If I'm talking about the variables, so what variables are we using for input here? What's the variable for input? No, the variable. Yeah, they're using x here, right? So they used x. And so now we got to say that's number of days. Number of days because x takes on those numbers. When it takes on the numbers, you need the unit. Okay? And that's our input. And then the weight, f of x. Right? Output, f of x, which is the y coordinate here. Okay. What does f of 60 mean? F of 60. Yeah, Eric.
Means 60 days since January 1st. John weighs 180 pounds.
Okay. But specifically, what does f of 60 mean? So everything you said was true about that, but f of 60 means what?
That is the output of f when the input is 60.
Okay, so now in the context then.
That means what I just said the first time.
Yeah, but the first time you just described the situation. What is f of 60? What is that thing?
John's weight after 60 days.
John's weight. It's John's weight after 60 days. So it's specifically, you said it, output. So what is the output? It's John's weight at 60 days after January 1st. Okay? Okay? All right. F of x equals 160. So then it says solve for x. So what does x represent in this expression? Where's Danny? What does x represent in that expression?
The input, basically the number of days after January 1st.
Okay. Which number of days?
Until he reached 160 pounds.
So the number of days that he was when he reached. So number of days after January 1st. How would you finish that then?
Until he gets an output of 160 pounds.
Okay. So when his weight was 160. Okay. So how'd you do on this? So what's your name right next to him? I forgot. Dana? Diana. What about the number of days after January 1st when his weight was 160? What'd you come up with? 120? Okay. I think you said one of them was. Is that what you said? So were there more?
Yeah, there's one more. 7.
170? Or a little bit less, like 168? Is that it? There's one more, right?
Yeah. More than 40.
Yeah, this would be 60 or 20. What? 15? Am I reading that right? So is his weight a function of the number of days since January 1st? Is his weight a function of number of days since January 1st? Yes or no?
No.
Oh, some are saying no, some are saying yes. Tell me your name again. Margarita. You said yes, right?
Yes.
Why yes?
But because for every there's a
She said for every input there is exactly one output. Is that true? Yeah, if we're talking about weight as a function of days, we're saying the input is days. It's always output as a function of input. Output as a function of input, or output with respect to input, or output in terms of input. So if our input is number of days, we pick a number of days and we ask the question, does he have just one weight at that time? Yes. You can't have, at any given moment in time, you can't have more than one weight. Okay? So is the number of days a function of his weight? So what's the input now? Weight. And so what's the question we ask? For any given weight, for instance, 160, is there just one time that he had that weight? No. Okay? Not a function. Okay? So, yes, weight is a function of the number of days, but number of days is not a function of weight, because if you pick a weight, there's more than one time that would have at which he had that weight. Okay, let's just go on to E. So E, evaluate f of 200 minus 160. So where's Caleb? I know there's a Caleb in here. Caleb, f of 200 minus 160, what did you think that was?
Change, like the difference of x.
Okay, so the change in, so it'll be change in, we got two quantities we're working with. Is it the change in time in days or the change in weight? Change in time of days. You're shaking your head. Tell me your name again.
Sarah?
Sarah.
It's the change in weight
How do you know that? How do you know it's a change in weight?
because f of 200 and f of 160 are both John's weight.
Okay? Yeah, so this is his weight after 160 days. This is his weight after 200 days. So if you take the difference of those two, you're going to get a change in weight. So which change in weight is it? So so is it any change in weight, or is it a specific change in weight? Yeah, but which change in weight is it? Tell me your name. Tyler. So does that make sense? So if I said between October and March, is that the way you would say it?
Yeah.
You usually say the first one first, right? So can you rephrase it? Yeah, so you said, yeah, so this is the final day, right? And this is the initial time. So if you're talking about a change, it makes most sense to talk about like from start to finish. You kind of said it the other way. So can you do it now? Change in weight from? Okay, you got it. That's okay? Anybody get an estimate from the graph? So you have to use the graph to kind of estimate this. How many? 30? So it would show up as what? From about here to about here? So is this f of 160, or yeah, f of 160 right here? And then f of 200. So that change in weight we can show by what? A vertical change right there. Delta y. So is he trying to lose weight or gain weight? We don't know, right? Could be one or the other, but we don't know. All right. Questions on these problems? So this is a really important thing for calculus. Not just cranking out values, cranking out numbers, but representing values that have meaning, right? So this is a meaningful value, right? So from day 160 to 200, how much did his weight change? Could have gone up, could have gone down. So that's using this function notation, that would represent that amount of change in weight. And that's a powerful thing to be able to represent and use that expression among other expressions and among, talking or writing or whatever, okay? That's why we practice it. So turn back a page. Number 2 on the previous page. Number 2 on the previous page. And I'm going to give you do A through D, and I'm going to give you an alternate version of E. Okay, so you're going to work A through D, and I'll give you an alternate version of E. I put the new part E up on the screen, so change part E to be that. This is what I need to do. Okay, talk them out with the person next to you. Talk about these. Practice saying it. Yeah. Sure. The name of the function, right? I told you h of t. So that's the name of the function. Like f is h, or like the last one we did was f of x. F was the name of that function that outputted its weight for a given time and day. So this is just what they named. They could have named it anything. They could have named it h or b or. Does that make sense? Okay, Derek, how'd it go? Let's do part A. So we're gonna regroup here. What'd you put for part A? What'd you think? So we want to represent the population K years after 1990. Say it again. So we want to represent it with a function notation. So we don't need the p equals part. So how do we represent with function notation the population K years after 1990? H of Lexi. H of K. Yeah, that's what. So that's right. If we want the population K years after 1990, well, that's exactly what the input is. The number of years after 1990. So our input is K, and then the output will be the population. Okay, Lexi, keep going. So what's H of K plus 3?
Function H is the input 3 plus 3 years after 1990.
So what? So the meaning. We want the meaning of the whole thing taken together. What is that thing?
The input, output, output.
Okay, so but in this context, what's the meaning of that? Right, it's an output. So when function notation gives output,
3 years after 1990.
but what is the output here? What is the output?
K plus 3.
No, that's the input. Tell me your name.
Davey.
Davey, okay.
B. The output.
No, population, you guys. Population is the output. It's the population of blackbird. So when you have an output of this function, it means the population of blackbird. Yeah. K plus 3 years. So the population of blackbird. When? When was it, the population? K plus 3 years. You have to be more specific. After 1990. See, K plus 3 years doesn't describe what's really going on. K plus 3 years after 1990. So what would be a different way to say this? The population of blackbird, if it's K plus 3 years after 1990, you could say it a different way. The population of blackbird in 1993. Is that right? What would that be? So how would I represent that? Population of blackbird in 1993. H of 3. So H of 3 would be that. So then, but you're on the right track. So what? H of K plus 3. Okay, you could think of it that way. So the population of blackbird 3 years after K years after 1990. Yeah.
Would be the population of blackbird after K years after 1990.
Yeah, so if we're adding 3, then that would be like maybe like starting in 1993, and then it's going to be K years after that. So the population of blackbird K years after 1993. Do you see? Which is the same as K plus 3 years after 1990. But first and foremost, it's a population of blackbird. The outputs of this function are populations at the given number of years input after 1990. Okay? How about a population that's 765 more than the population in the year 1996? Michaela, did you get this one? Nice and loud.
K plus 6
K plus 6.
plus 7.
Like this? This is what I heard. Like that? What do we think? Adam. Okay, what do you think? There's no F. There's no F here. K plus 765. Oh, I guess this is a good question. K of 6, I'm hearing. H of 6 times 765. I'm just writing down what you guys are saying. The population in 1996 is H of 6. H of 6 is the population in 1996. Now they're saying 765 more people than that. So you're going to add to the output. You're going to add to the output. That's a 6, not a B. Does it make sense? Okay. All right, and what about this? The change in population from M years after 1990 to M plus 7 years after 1990. Is it Nick? Matt, sorry.
Close enough.
I had a high chance. Okay.
H of n plus 7 minus h of n.
How did Matt do? This is the change in population starting from M years to M plus 7 years after 1990. How do you do? Good? You did good. All right. There's a different way to kind of think about this, right? Because, all right, let's pretend we were graphing it. Here's our number of years. And what's the starting number of years after 1990 here? Starting number of years? M. That's our starting number of years. And our ending number of years? M plus 7. So what's going on here? Starting M, ending M plus 7 years after 1990. What kind of observation can you make? What's that about?
Wouldn't it just be h of 7? In that case.
Okay, you're kind of going on a different track. I'll talk about that later. But so what's going on here if we start at M years after 1990 and we finish at M plus 7 years after 1990? What is this about? A change of how much? 7. That's a change. And so how can I represent that? We've got symbols for that. Delta what? Delta M equals 7. Okay, so this is, when you see this expression, it involves a delta M, or a change in the number of years, of 7. So we can use that to kind of rephrase this. So this could also be said the change in population So rather than saying starting at M years and ending at M plus 7 years, we can make use of this idea that it's a what? A change of 7 years. So it's the change in population over the 7-year period. Which 7-year period? What's that? Yep, between M and M plus 7, or starting M years from 1990. So we could say, talk about the time. Rather than talking about starting at M and ending at M plus 7, we could say it starts at M and it lasts how long? 7 years. So that would be an alternate way to say it'd be the change in population over the 7-year period beginning M years after 1990. We recognize that in the shadows here is a change of time of 7 years. So we can express it that way. So now I want you to try E again. See if so now that we've talked about that, E is based on that. So see if you do E again. Go. See if you can do it.
Do you want me to walk around?
No, it'd be quick. Okay, Sebastian, you're up. Any progress on this? So let's talk about, so when is this period starting? When's the starting of the period? Okay, so how can you represent the population in 1991? The population in 1991. That's, tell me right there in the glasses.
Yeah.
What's your name? Matt. Population in 1991.
What do you want?
The population in 1991. Ashley. H of 1. And so will that be the first? Would we do H of 1 minus something or something minus H of 1? Okay, so if the starting time is 1991, that's going to be a population minus the population in 1991. So what population minus H of 1 will give us H of what? Yeah. H of T. So how do we, we need to express any number of years. I heard K, let's use K. But that was up to you, okay? So you need to express just some number of years. So if we want the change starting in 1991 and then lasting K years, what is our final time? Okay? Is that right? That's not right. We need a change of time of K. So let's draw a picture that will help. So we're looking for the final time, and we need this to be delta T equals K. So what will the final period of time be if we start at 1 and then we have a change of time of K? Adam? H of, right, K plus 1. See, to get a change of time of K years, starting from 1, it's going to be K plus 1. And that'll give us a change in time of K. Okay, so you're going to have lots of practice of this in web work. This is important, that you can make sense of these two quantities changing together. So starting in 1991, we changed time by K. The population will change that much in that time. Questions? Yes, sir. Tell me your name. Braden.
Would we want to just be H of K because it says any, so if we wanted to find out, even though it'd be 0, but the change was between the year and the year itself, that's part of the data set that we should be using.
I don't think he's asking about going backwards. I think he's more talking about going forward in time. Like, so the years after 1991, not the years before 1991.
Well, here's the key, that it's starting. It's a period of time starting in the year 1991. So if we start in the year 1991 and it lasts for K years, then the end of that period of time has to be K plus 1. Does it answer it?
Yeah.
Are you sure? Yeah, because if you just do H of K minus H of 1, Well, h of k would be measured from 1990. So, how does that seem to work? Oh, right. So h of k would be, it's kind of too hard to, this is k plus 1 if this interval is k. If you do h of k, then that's some value right here. H of k is like, for k years after 1990 is actually in the middle of our interval. And so h of k doesn't make sense because it's halfway, it's like in the middle. But if you start at 1 and you have a change of k, you end at k plus 1. That's the bottom line. Okay, so let's look at this example. Okay, so Colton, you're up. Do you agree with 1 through 3, first of all? So how did you go about number 4? So how many accidents would be expected in a year where 65 workers are employed daily? Can you talk me through what you did?
To function G.
Function G.
Where it says 65 workers.
Okay.
Looked at the output, it's 12 hours.
12 hours.
So then we went back to function F, and looked at 12 hours, and looked at the output of 12 hours, which was 13 cents.
So your answer is?
13.
How'd Colton do? Agree? Yes. Okay. So how about 100 workers? Is it Nicholas? Is that right? Are you Nicholas? Tell me. How did you find the accidents expected for 100 workers? Nice and loud. In which function? G, okay. Eight-hour shifts. Okay. So you said 6. How would we represent those with function notation? How about Tyler right here? Can you do that with function notation? Like this first one. That 65 workers results in 13 accidents. So we start with here. So 12 is, how can we use just 12 in function notation? Output of G, when the input is? And how do we express that? 60, 65. But then we take G as 65, and that is the input into F. So now that whole output of G, listen, that whole output of G becomes the input of F. So it's like we're taking a string, a process, a two-step process, where the output of the first function becomes the input of the second function. And so doesn't that notation do that? The output of G is now the input of F, in the parentheses of F, right? So what's the value of F of G of 65? 6. Okay, this is the idea of, sorry, 13, thank you, 13. Stringing two processes together like this, where the output of the first is the input of the next, is called composition. Composition.